However, the computational cost of deep networks, both in training and inference modes, presents challenges to deploying these algorithms broadly. Research into reduced precision networks and compressing trained networks seeks to reduce the computational cost of using deep learning. However, streamlining the communication within deep learning systems is also widely impactful. This paper presents a new technique for training networks for low-precision communication. Targeting minimal communication between nodes not only enables the use of emerging spiking neuromorphic platforms, but may additionally streamline processing conventionally. Low power and embedded neuromorphic processors potentially offer dramatic performance per watt improvements over traditional von Neumann processors. However, programming these brain-inspired platforms generally requires platform. Today, the majority of artificial neural networks have not operated using discrete spike-like communication. We present a method for training deep spiking neural networks using an iterative modification of the backpropagation optimization algorithm. This method, which we call Whetstone, effectively and reliably configures a network for a spiking hardware target with little, if any, loss in performance. Whetstone networks use single time-step communication and do not require a rate code or other spike-based coding scheme, thus producing networks comparable in timing and size to conventional ANDs, albeit with binarized communication. Whetstone on a number of image classification networks, describing how the sharpening process interacts with different training optimizers and changes the distribution of activity within the network. We further note that Whetstone is compatible with several non-classification neural network applications such as autoencoders and semantic segmentation. Whetstone is widely extendable and currently implemented using custom activation functions within the Keras wrapper to the popular TensorFlow machine learning framework. Introduction. 1.1 Overview and Motivation Artificial Neural Network and Algorithm. Specifically, deep convolutional networks, DCNs, and other deep learning methods have become the state-of-the-art techniques for a number of machine learning applications. And audio processing has made their use essential in many domains. Some applications such as onboard processing and autonomous platforms like self-driving cars, drones, smartphones. The resource requirements of running large ANDs may still prove to be prohibitive for 5. Large ANDs with many parameters require a significant storage capacity, which is not always available. And data movement energy costs are greater than that of performing computation, making large ANDs intractable. 6. Additionally, onboard processing capabilities are often limited to meet energy budget requirements, further complicating the challenge. Performing computation locally rather than on a remote server. Efficient AND calculations seeks to facilitate moving ANDs into resource-constrained environments, particularly for trained algorithms that simply require the deployment of an inference-ready network. The current generation of specialized AND processors gain advantages simply by customizing key computational kernels for ANDs in application-specific integrated circuits, ASICs. TPU, the Intel Nervana neural network processor, and the NVIDIA A Volta GPU architecture with dedicated Tensor Cores 710. targeting deep neural network inference enable impressive numbers of cells do not fully capture the emerging landscape of neural network architectures. For instance, it has been shown that the number of MACs is not indicative of the energy consumption of a DCN 1112. And so hardware supporting high operation counts, rather than optimizing a key computational kernel, further benefits will likely be realized by hardware platforms that implement versions of ANDs that are mathematically optimized for efficient performance, such as using low-precision weights, minimize memory costs, and discrete activation functions, minimize communication costs. One such promising technology is neuromorphic hardware, which has been shown to be capable of running ANDs and can potentially offer orders of magnitude lower power consumption, performance per watt, than more conventional digital accelerators 13. While there are a number of approaches to neuromorphic hardware, most scalable current platforms such as SPI-Naker and IBM TrueNorth achieve low power performance by coupling spike-based data representations with brain-inspired communication architectures 1318. For spiking neuromorphic hardware to be useful, however, it is necessary to convert an ANN, for which communication between artificial neurons can be high precision, to a spiking neural network, SNN. Spiking is a generic term describing the abstraction of action potential formation in biological neurons crossing a voltage threshold. What spiking means for SNNs varies considerably, but at minimum it requires that neurons only communicate a discrete event, a 1 foot or nothing. In addition, many approaches to SNNs leverage time, or when the spike occurs, as a key state variable to communicate information. In this paper, which focuses on the first step of mapping SNNs to static ANN applications like image classification, we define spiking as the simplest activation function for neurons that is compatible with neuromorphic hardware, a discrete 1 or 0 threshold activation. For static ANN applications, this time-agnostic approach is sufficient, and in fact desirable for reasons of throughput. However, for dynamic applications such as video processing, it is likely that the time dimension offered by spiking will be useful, though that is beyond the scope of this study. The conversion of ANDs to SNNs, whatever their form, is non-trivial, as ANDs depend on gradient-based backpropagation training algorithms, which require high-precision communication. And the resultant networks effectively assume the persistence of that precision. While there are methods for converting existing ANDs to diminish the benefits of spiking, here we describe a new approach to training SNNs, wherein the ANN training is to not only learn the task, but to produce a SNN in the process, specifically between nodes. The training process of a SNN can be nearly as effective as a comparable ANN. This method, which we term whetstone, portrayed in Fig. 1, inspired by the tool to sharpen a dull knife, is intentionally agnostic to both the type of ANN being trained and the targeted neuromorphic hardware. Rather, the intent is to provide a straightforward interface for machine learning researchers to leverage.
Hey, Speechify here. You have exceeded your daily HD word limit. In order to continue enjoying your experience with high-quality voices, please upgrade your subscription by clicking the upgrade button. If you are not ready to upgrade, you can continue listening with non-HD voices.
To leverage the powerful researchers to leverage the powerful capabilities of low low-power neuromorphic hardware on a wide range of deep learning applications. See methods for applications. See methods 4.4. Method